And so we'll move on to the next talk, which will be by Sandra from EPFL.
Sorry, I'm at Imperial now. I'm at Imperial now.
So, sorry, my mistake. She has now moved to Imperial College. Also, I see that not a lot of people are actually being able to maybe ask questions on Tulip. So maybe for the next two talks, I can allow a question to be asked by coming here, but you'll have to speak and come here all the way, walk down, and ask the question. If I do not have any online questions, then we can do that for the next two talks. So yeah, you can start.
Hello. Hey everyone. Today I'm going to talk about our work on evaluating practical QUIC website fingerprinting for the masses. And this is joint work with Ludovic, Chris, Marwan, Nick, and Carmela. I think we already had a bunch of talks that explain a lot of things like website fingerprinting and QUIC and defenses and so on. So this is going to make my job a little easier, and I'm going to breeze through the intro a little bit. So a website fingerprinting attack is basically one where you have an adversary that's monitoring the channel between a client and a destination, and this channel is encrypted. And the adversary aims to identify which website is being visited by the client, so the adversary doesn't have access to the content of the traffic and instead sees like a sequence of packets. And the idea behind website fingerprinting is that different websites have different kind of resources and structures. So the kind of traffic patterns that an adversary observes is very different for, let's say, example1.com and example2.com. Oops, sorry. And generally, in a website fingerprinting attack, you use some sort of a machine learning classifier to distinguish between these traffic patterns. So a typical website fingerprinting pipeline, you have some sort of a traffic sample. The adversary extracts certain features from this and uses that to train a classifier, which they can then use to identify other web pages that the client may visit in the future. And the kind of characteristics that are used, you don't have access to the content of the traffic anymore. So the adversary relies on the metadata, so things like directionality, the size, the timing, or any kind of header information that is not protected by encryption. So we are looking at website fingerprinting on the QUIC protocol, which is a protocol that was standardized a couple of years ago. It's a UDP-based protocol, and it's seeing a lot of rapid adoption. I think as of last month, of the top 10 million websites, about 26% of them have already adopted QUIC. And I just want to highlight that website fingerprinting on QUIC has already been done. So there was prior work by Smith and co-authors that found that QUIC is susceptible to website fingerprinting, and it's no more or less difficult than fingerprinting, let's say, TCP-based protocols. We were more interested in looking at the defenses against website fingerprinting for QUIC. And if you look at the QUIC RFC, it actually specifies that the QUIC protocol has a padding frame, and this frame can be used to add padding to the QUIC packets so as to, reduce the kind of size information and provide some kind of a defense against traffic analysis. So Smith and co-authors also did do some work on website fingerprinting defenses. So what they did was they built a mechanism called QCSD, which is a mechanism that uses these padding frames. And this can be implemented on the client. And these padding frames can then be used to implement any kind of defense that already exists or new defenses that can come up using this frame. And so this is more of a framework that allows you to design a particular defense. And we were interested in looking at specific defenses and how these work against the QUIC protocol. And what we've seen is that even in Smith's work or in prior work on defenses, generally these have been applied to a VPN or a Tor scenario. And we wanted to kind of look for the masses, that is the average user that may not necessarily use VPN or Tor. And the other point I want to highlight is we wanted to look at the practicality of these defenses, whether they're actually going to be implemented or will they see widespread adoption for the average user. So if you look at the adversarial model, so let's say that you have a number of ASs or autonomous systems, and you have a client that is located in a particular AS. And this client can access different web pages which could be hosted on somewhere else in another AS. I've put them all on the same AS, which was a bad idea, but they could be hosted on different ASs. And this traffic may follow different paths which can cross several ASs. And you see that there are these vantage points, which could be middle boxes or routers that are located, that can observe this traffic. So in our scenario, the adversary is any AS that is on the path between the client and the destination host. And these vantage points may not necessarily have the capability to run website fingerprinting attacks, so they might mirror all of their traffic or some of their traffic to some centralized server for processing and running the attack. Now, one question that you may have is, if you don't have Tor or VPN, can we not just use IP addresses and identify which web page is being visited by the client? And this is true. I mean, if there is a one-to-one mapping between the IP address and the host, then you don't have to do this attack. But generally what we see is that there is an increased penetration of CDNs and co-hosting on CDNs. So the kind of adversarial model that we are looking at is the adversary is trying to identify the correct web page amongst all the web pages that are hosted behind a CDN IP. Now, if you look at defenses, we can broadly categorize these defenses into two. One are application agnostic defenses, which is just using padding or timing without any information on the website that the defense is meant to protect. And then you have other category of defenses, which is application aware, where you need some information about the website, like the sizes or the types of resources or the ordering, in order to tailor the defense based on the website that it's protecting. So we first looked at application agnostic defenses. And basically the process is that we have the website fingerprinting pipeline as before. We apply some defense, and then we see the performance of the classifier to see how well this defense works. And we built a QUIC dominant data set. That means that all the websites, because QUIC is still being adopted, it is difficult to actually build a set of websites that primarily use only QUIC traffic. And we build a set of about 150 pages. The size is based on partnering with Cloudflare and looking at generally the sizes of clusters that are found on the CDN. And we used the K-fingerprinting features and a random forest classifier in order to see which kind of features are most relevant for the defense. So in our classifier, we have 150 sites. So a random classifier, you have 1 in 150 chance of getting it right, which is the baseline. So if you look at the undefended traffic, you see that the classifier actually obtains like a 96% F-score. The precision and recall are around the same here, which is much higher than the random baseline. Now, if you look at the features that are generally used by the classifier, you see that the sizes of the packets are very important. So things like total number of bytes or specific, the frequency of certain sizes really turn up on the classifier. So what we did was first we applied the padding frame in order to hide some of these size-based features, not just individual sizes, but also padding to increase the size of the trace as well. And we see that the F-score drops by like about 12% or so, but it is still much higher than the random baseline. And if you look again at the features that the classifier is using, you see that it's because the directionality-based features became very important. You still have things like total number of packets that the adversary relies on. So in order to tackle that, we implemented dummy injection, which is, again, inserting padding frames and dummies. And we used a popular dummy injection defense called front. And what we essentially see is that even with varying different parameters of front, you need to have a very high overhead in terms of bandwidth in order to obtain some semblance of protection. So if you want to get about 70% F-score, you need to essentially double the amount of traffic that you are sending. And we also did this for constrained adversaries. We assumed we wanted to see whether defenses are more effective if the adversary has limited traffic visibility or limited processing power to process these traces. And I don't go into the details of this, but basically what we see is that when the visibility is limited, there are just a couple of ASs. For example, the large prevalence of Google scripts on many web pages means that just using timings of Google resources can already be like a very low-cost fingerprint for an adversary. And we also did this for limited processing, where we did the attack against sample net flows instead of individual packets. And basically, the sort of conclusion of this attack is that most of the privacy gain actually comes from the limitations of the adversary, but the defense itself does not really particularly add some benefit. And this is mainly because application-agnostic defenses are failing to hide global features. So these defenses do not know the size of the website in advance in order to know how much is the optimal amount of padding that can be added so that you have effective bandwidth and as well as effective protection. So we looked at application-aware defenses, and we studied basically structure of different web pages where we wanted to see the prevalence of first and third parties on different web pages. And the main thing we found was that nowadays websites have a lot of third-party resources on their web pages, especially Google resources. And we did a bunch of experiments and found that all the parties have to coordinate if you want any kind of protection of resources and protect against this website fingerprinting. And we did application-aware defenses, the same kind as before, which is size-based and dummy injection, this time knowing the sizes and the ordering of resources. And essentially what we found is that dummy-based injection, if you know the application in advance, does reduce the F-score and with better bandwidth than application-agnostic defenses, but it is very difficult to implement with the current state of the internet because you need coordination of a large number of parties. So I'm going to end this talk on sort of like a negative note, essentially, because it seems like if you want to defend against website fingerprinting, if you use application agnostic, then there's a lot of overhead. But if you want to try to do application-aware defenses, then you need coordination of a large number of parties, and this is almost impossible with how the internet is structured as now. But there are a few things we can look at. We can think about coordination among standards bodies and browser vendors and the parties, about looking at standardizing resources on websites. And finally, there's also a lot of work, including the previous talk, which was about connection migration and things like that, where we can layer defenses, where we can have padding, but also things like rotating connection IDs to remove linkability between packets. Yeah, that's it. Thank you.
Thank you so much for the talk. I think we have time for one question, and we also have it on Zulip. So the question is, are you assuming that training and testing are done on the same network? What would be the impact if training is done on a network and testing is done on another network?
Yeah, in our experiments, we did do the training and testing on the same network. We did try a few things we did try varying a few things like using a different client or using what happens if you change the time of the day that you collect the traces and so on, but we did not experiment with training on a different, testing on a different network. But generally from our experiments, it looks like there could be some reduction in the performance, but not by a lot, at least if you change the network. Yeah.
Thank you so much, and yeah, thank you for the talk. And